Hello and welcome to the third talk of the Warwick AI Summit. The Warwick AI Summit is a series of talks and workshops on a wide range of topics that share the common theme of machine intelligence and the conflicts, applications, and implications of the introduction of machine intelligence into our world. The aim of this summit is to draw attention to the pace at which AI is rapidly changing the world in which we live, and to broach the difficult and exciting questions that are arising, all in an attempt to cultivate more discussion and thought among the next generation of researchers and consumers of AI. If you're not already involved in Warwick AI, I'd urge you to check out the links down below to take part. We run workshops and classes teaching practical skills. We offer guidance for starting up your own AI-based projects, and we have a careers team that are dedicated to helping you find work in what I consider to be the most exciting and future-proof of industries. We also host events with academics and professionals who are using artificial intelligence to revolutionize the way that work is done in their area. So today we're speaking to Toni Creswell from DeepMind. Just before I introduce Toni, I'd like to introduce my co-host, Shannon.
Hi, I'm Shannon. I'm working with Warwick AI as well. I'm running talks, delivering insights into AI research and applications. I found out about DeepMind when I was 15. Having heard about AlphaGo for the first time, I was inspired, and it is what led me to join Warwick AI.
Thank you, Shannon. And the reason that you're all here, the main guest of the event, and Toni Creswell. Toni is a research scientist at DeepMind, and after receiving her PhD in deep learning and computer vision at Imperial, she's gone on to work with DeepMind, researching how we can instill perception into intelligent machines. So today she's going to be giving us an insight into the fundamental research that's happening in the sphere of artificial intelligence today. If you've ever wondered what goes on in AI, the research that's happening, or what it's like to work for one of the world's leading AI research laboratories, then Toni is the person to speak to. Please make sure that you post your questions in the chat for a chance of winning an official Warwick AI hoodie, which Toni is going to give to her favorite question at the end of her talk. So without further ado, I want to hand you over to Toni. Thank you, Toni.
Okay, yes. So yeah, this talk is going to be about some of the recent developments in AI research. So hi, everybody. Thank you so much for having me here. As has already been mentioned, my name is Antonia, and I'm a research scientist at DeepMind, where I'm really interested in helping agents and AI better understand about objects. And while this may seem very simple to us, objects are things we interact with every day, it's actually surprisingly difficult to get agents to really understand about objects. And this is actually quite a common theme in AI. There are things that we really take for granted, and it's actually very difficult to get AIs to do these things. So yeah, I'm really excited to be sharing today some recent developments in AI research. Okay.
We'll just get the slides open. That's the one. Perfect.
Okay, so now I have my slides up. What we're going to cover today, I'm going to talk about some historical examples of AI. I'm also going to talk about what's enabled some of the recent advancements towards AI. Then I'm going to talk about some recent breakthroughs, and I'm going to finish with an insight into my own research, which I hope you'll find interesting. So let's start with some historical examples of AI. So very brief history. In 1997, Deep Blue, a computer algorithm for playing chess, beat the world champion at chess. In 2011, IBM's Watson defeated the Jeopardy quiz show champion at this quiz game. And in 2015, a particular ResNet outperformed humans at image classification, which is pretty impressive. And as mentioned a minute ago, in 2016, AlphaGo beat Lee Sedol, the world champion at Go. And Go is a very complex board game. So having seen these examples, you might think to yourself, oh, artificial intelligence is solved, right? But maybe it's not. So the best way to really start thinking about artificial intelligence is to start thinking about human intelligence. And there are really so many elements to our intelligence. There's perception. This is how we see the world, how we hear things, even how we smell, taste, and feel the world. Attention. This is what allows you to hopefully focus on my voice rather than letting any background noise distract you. Navigation. This is how you move around space, how you get up from your bed in the morning to brush your teeth, how hopefully in normal times you're able to get to work. Also transfer. So this one's actually really key, and I'm going to come back to this one actually a few times. So as humans, we're very, very good at learning one set of skills and then using them in a different setting. So one really simple example is if you learn how to write with one pen, you can probably write with a different pen. And that's probably something that we really take for granted, but it's something that our agents find surprisingly hard to do, to be able to generalize skills from one setting to another. Multi-agent. So we interact with an environment full of other agents. These might be our friends, our colleagues, our teachers, our parents. And in fact, we depend a lot on interaction with others for our learning. One really great example of this is imitation. So imitation, this is where we see how other people do things, and then we try and copy them. So a personal example is, so I recently started to learn how to climb, and quite often I have to ask my climbing partner to demonstrate some moves to me so I can try and copy them and then move on and learn some new skills. So other important element of our intelligence is planning. So this just involves, for example, thinking before doing something. So making a shopping list, packing for holiday. There are many different examples of planning. Language. So this one's really fascinating. So we use language to communicate, and this is not just verbal language. We also use body language. For example, we might point at something that we want. I might smile to show you that I'm happy or that things are okay. Another really key thing is imagination. I think this is one of the really crucial parts of human intelligence, because we don't have to actually do something to know what the outcome of doing that thing might be. One really obvious example, or one really crucial example, which helps keep us safe, for example, is we don't need to step into a road with moving cars to know that that's really not a good idea. We can imagine that that would probably really hurt and that it would be a bad idea. And so we can just avoid doing it. Another important aspect is prediction. So this also kind of plays in with imagination as well, but we can also use it, for example, if you're playing catch with a friend, you predict where a ball is going to go in order to catch it. And then finally, but certainly not least, is memory. And memory plays all kinds of different roles. We have both long and short-term memory. Long-term memory allows us to do things like recall the name of our friends, while short-term memory allows us to do things like adding two numbers together in our head. So when we look at this diagram, it's very easy to see that there are very many aspects to our own intelligence. And there's probably far more, in fact, there's definitely far more than what I've been able to show here in this diagram. But one of the most interesting examples here, as I kind of mentioned before, was transfer. So humans are very, very good at doing many different tasks. If we think back to some of the examples on the previous slide, so for example, Deep Blue. Deep Blue is actually only able to play chess. It's not able to transfer those chess playing skills to play some other kind of board game. For example, it can't play chess. Sorry, it can't play checkers. It definitely can play chess. It can't play checkers, and it definitely can't play something like tennis. Another example is Watson. So Watson was trained with data from many dictionaries and thesauruses and other texts. And Watson might be able to answer all sorts of questions, but it's not grounded in the real world. So you might be able to ask Watson what color honey is. And it may be able to answer yellow. And Watson may even know about other yellow things, but it's never seen honey, and it doesn't know what yellow really means because it's not grounded in any kind of perception of the world. And then also we talked about a particular ResNet on the previous slide, and I'm talking very specifically about that ResNet. So that particular ResNet is only able to categorize objects from a very specific number of classes, while humans are able to categorize objects from many, many more classes. And what's very cool is that we're still able to learn new categories. We're not limited to the few, even if it's 1,000, the classes that we've been told to learn about. And one of the very cool things is that as humans, we're also able to learn new things very, very quickly. As infants, for example, we only have to be showing a few examples of what a dog is before we can then point out all the different dogs that we see. And today, there are many researchers focusing on different elements of human intelligence, and great progress has been made to kind of introduce these into AIs. So, okay, so now I'm going to start talking about what has enabled advancements towards AI. So something super exciting happened in 2012. ImageNet is this really large data set of natural images. It includes images of objects from 1,000 different categories. These are things like cats, dogs, bicycles. It even contains subcategories, so different types of dogs. And researchers interested in image classification use this data set as a benchmark to evaluate their models. And just to be clear, image classification means you show an AI or a computer an image, and it predicts the label for that image. And this diagram is showing classification errors for different models, actually the best model from each year, where the lower the error, the better the model. So what you'll notice here is that there's a large decrease in error between 2011 and 2012. So what's happening here? Well, two things. So AlexNet, this 2012 model, actually uses deep learning rather than handcrafting features. And I'll talk a bit more about this on the next slide, but this means that AlexNet learns from many, many data examples, avoiding the need for handcrafting, which can be very brittle. But the other really important thing, which many deep learning people are very, very grateful for today, is AlexNet leveraged GPUs. So these GPUs allow us to compute very many operations, computational operations in parallel. And this significantly reduces the computation time, allowing us to use much larger data sets for training and to actually train our models in a reasonable amount of time. And in fact, all the models here shown in blue use deep learning. And you can also see here the ResNet that I was mentioning earlier, 2015, is the one also uses deep learning and is the one that outperformed humans. So yeah, really the key things were that GPUs enabled us to train really large, deep learning models on huge amounts of data. So let's now just explain what the difference between handcrafting and learning systems are. So handcrafting relies on hard-coded knowledge. So this requires a bunch of experts to get in a room, or many rooms, and think about kind of hard coding in knowledge for a particular problem. But this means that actually these models are not able to deal with unexpected input, and they're really limited to pre-programmed solutions. So this is actually kind of an example I pulled off the web, but it illustrates this problem. So here the question would be, what is your favorite room in the house? And it has prepared answers for kitchen, bedroom, living room, and then everything else, it just gives a generic response. So if it asked me this question and I said, oh, my favorite room is a TV room, then the response is going to be, oh, maybe you prefer to be outdoors. But that response doesn't actually really match the answer I gave. And so this is a really classic example of where these systems can be very brittle if they receive unexpected inputs. So learning systems, on the other hand, these learn from experience and from data. And these actually can generalize to new tasks. And what's super cool is that they can solve things that we don't even know how to. As long as we have data, the models can just learn to solve whatever problem we're trying to solve, provided we have data. And one other interesting thing is that a lot of people say that the learning systems are slightly more inspired by neuroscience, and this works at many different levels. Okay, so here's a further example of really the difference between a handcrafted system and a learning system. And in both of these examples, we're trying to do image classification. So in the handcrafted example, this top one, we take an image and we extract features using handcrafted methods. And this might involve applying a number of handcrafted filters to an image to detect maybe different object parts, maybe to detect edges. And then we use these features, we pass them to a classifier to try and predict a label. But imagine for a moment that the classification task was between cats and dogs. It might be really hard to come up with a set of filters for distinguishing cats and dogs. If you take a minute for yourself and just think how you might go about describing the differences between cats and dogs, that's actually something that's very difficult to do. And what's even worse, we might manage to do that, and then we might decide, oh, we actually also want to be able to classify cows. And that would mean that we would have to redesign all those filters, or at the very least, add new filters. And so we can really just avoid this problem if we learn features rather than handcrafting them. So that's the example at the bottom here. So if we directly feed our image to our model and predict the label, we leave it up to the model to learn the features that best suit the task. And this is essentially at the heart of learning models. So here is an example of a deep learning system. So here we're looking again at the classification task. So we have some kind of input image. We're going to pass these through many layers of learnable parameters or filters. I personally like to think of these as filters, but you can just think of them as something that you pass some input through, you get an output, and you can continue to pass your input through these many different layers of operations, and then you get some kind of prediction. What we see here is that the model was predicted that this is a dog, which is not right. The truth is it's a cat. And so what we can do is we can compute some kind of error, and then we can update all the layers of these networks to try and minimize this error. And what's very cool when you do this is that this really means the model's learning filters that help it perform the specific task that you want to do. And of course, if the task changes, you can just continue to train the model to update the weights or these filters differently. And also what's important is that we actually repeat these steps many times with many images. from as many classes as you want your classifier to work on. Okay, so what's kind of cool is this. So this is showing some examples of what these systems learn and what's actually in these filters. So these are visualizations of the filters learned by these kind of models. And these images are actually taken from this website at the bottom here, which I really suggest you check out, because the visualizations are really amazing. And it gives a bit better insight into what these models are learning. So what we see is these are visualizations from the first couple of layers. And what we see is that these networks are really learning to detect edges and very local textures. So we see that the model is kind of picking out fine points, some kind of grid-like structures, some edges, and maybe some kind of fur-like texture. As we move to layers further down in the network starts to detect parts of objects and much more complex patterns as well. So, for example, these might be detecting books on a shelf, maybe some phones. This next one here is more clearly capturing the eyes of some animal and maybe some fur. These filters here are capturing some architecture, some windows and doors. And this filter is probably capturing something about bike wheels. So we've just seen examples of deep learning used to perform classification tasks, but we use deep networks, or we can use deep networks to learn all kinds of different things. So I'm illustrating a few examples here, but really there are lots of different things you can imagine doing with deep networks. So the first example here is we can learn to predict the next frame in a video. So if, for example, you imagine your input to your network is the frame at one time step, you can actually train the model to predict what that frame will look like at the next time step. Another nice example is we can use these models to learn to remove noise from an image. So, for example, the input can be some kind of corrupted image, and we can train these models to learn to produce clean versions of those images. Okay, and the final example I'm giving here is really going to lead us into the next section, where I'm going to talk about some of the recent breakthroughs. So this example here is showing that we're actually able to learn to predict reward associated with taking an action from a given state. So if in this case the minion is our agent, and its current state is that it stood in front of a brick wall, and it has two options of what action it can take. It can turn left, and it will probably get a negative reward, or it can turn right and get a much higher reward because there are bananas there and minions like bananas. So we can actually train networks to predict particular rewards associated with taking actions from a particular state. And this is linked a lot with reinforcement learning, which is what I'll talk a little bit in the next couple of slides. Okay, so yeah, now I'm going to start to cover some recent breakthroughs, and all of these methods use deep learning in some creative and exciting ways. Okay, so the DeepQ network is a really exciting early example of combining deep learning with reinforcement learning. So I'm going to first explain what reinforcement learning is. If we look at this diagram on the left, bottom left here, what we see is we have some agent and some environment. And what the agent does is it gets observations from the environment. And given those observations, it can choose to take actions in the environment and then receive updated observations and rewards, depending on what actions the agent took. And in a typical setting, what you're wanting to do is train an agent to try and maximize reward. And the agent in this case can actually be a deep learning network. The DeepQ network, DQN, here, this model is being trained to play many different video games. So the approach here was to take raw pixels as input. So you take the visual raw input from these Atari games, you pass them through a deep network, and then you train the network with reinforcement learning. And what's very cool about this is that it enabled a single agent or a single algorithm to achieve human level performance on 49 different Atari games with just one architecture. And this was really an exciting promise for deep reinforcement learning. And this is really what's led to a lot of other work in deep learning. And just to tie this back in with that slide earlier, this is a really great example of one architecture being able to be used for many different tasks. Here, one architecture can be used to play lots of different types of games. And if you're interested for more details, I strongly suggest you check out this paper, Playing Atari with Deep Reinforcement Learning. So still on this theme of being able to play multiple games with a single algorithm, I'm introducing AlphaZero here. So traditional programs used for playing games like chess are far stronger than any human world champions. However, they have this same issue that they really rely a lot on handcrafting. So they have hundreds, if not thousands, of heuristics and rules hand programmed by teams of programmers and grandmasters that tell them how to evaluate positions and what to play. In contrast, AlphaZero starts off with a blank deep network and no knowledge. And it actually learns to play chess by playing millions of games against itself. And to begin with, it plays completely randomly. But every time it wins, it adjusts the weights of its network so that the next time that it's in a similar position, it will be more likely to take similar actions that allowed it to win last time. And the really amazing thing about deep networks is that they're able to generalize to new situations. So AlphaZero can be used to learn to play other two-player, we call them perfect information games. That mostly just means you know what other moves the other player took. So that the program can learn to play lots of different types of games. So chess, shogi, which is a kind of Japanese version of chess, and also Go. So it's a system that's generally able to play different games. And this figure here is kind of just to demonstrate this model's performance. So here, each of these are hard-coded baselines that strongly outperform the best players. And we see that this model is able to perform very well. Okay, so slight change of direction here. So this is not looking so much at reinforcement learning, but one model or kind of area of research I think is really interesting are these relation networks. So one aspect of our reasoning or our thinking is being able to reason about different objects, knowing that one object is bigger than another object, knowing that one object is on top of another object or inside another object. And what relation networks allow you to do is learn relations between objects or between things, which is very cool. So an example of this being used is with this relational questioning kind of data set. So here, given this image, we might ask the system, are there any rubber things that have the same size as the yellow metallic cylinder? And so to solve that question, you would need to find that yellow metallic cylinder and compare it to all the other objects in the scene and reason about the yellow metallic cylinder with respect to the other objects. And this is really what relation nets enable us to do, which I think is very interesting. Okay, so generative models, which is an area that I looked at quite a lot during my PhD. So before we even begin to talk about this slide, have a look at these images and try and figure out which of these images are real and which of these have been generated by a machine. So maybe you think that they're all real, but actually all of these are fake images output by a machine. And what's really cool about generative models is that they actually allow us to learn without the need for this labeled data. So you might have noticed when we're talking about these classification models that we really needed these images, but what we needed along with the images, if we wanted to train models for classification, was lots of labels. So, but getting labeled data can be very difficult. It's much easier to get images without labels than it is to get images with labels. And so we can actually train generative models without the need for labeled data. And this can help us, and we can then use what we learn in those models for downstream tasks. And one quote I really like, which I think kind of ties in nicely with generative models, is one from Richard Feynman, which says, "What I cannot create, I do not understand." And so you can kind of think in a way of these generative models trying to generate images, some of that understanding of images being kind of imprinted in the weights of the network or the filters of the network, and then being able to use that for downstream tasks. Okay, so now I'm going to move on to talk a little bit about my own research and some of the things that I personally find very interesting in the field of AI. So I'm really interested in machine perception. So yeah, if we go back to this figure here, perception is something that really excites me and something that a lot of my research really focuses on. But I'm also interested in how perception interplays with memory and also kind of prediction and imagination. So, okay, so many of you are probably familiar with our furry friend, the domestic cat. And while you might admire how cute and fluffy the domestic cat is, you probably haven't realized quite how intelligent they are. And in fact, maybe it's unsurprising now by the end of this talk, or towards the end of this talk, but the domestic cat is significantly more intelligent than some of the most sophisticated modern AIs. Okay. So here what you're seeing is a cat, a human interacting with a cat where the human hides a ball underneath one of these cups and then pushes all these cups around, and then the cat's able to find that ball again. So at the very highest level, what's going on here is some kind of object tracking. The cat's able to keep track of where the ball is, even though it can't see it anymore. But before the cat can even do any kind of object tracking, first of all, it needs to know that there are even objects. So it needs to understand that there are these cups, that all these cups are different individual objects. Maybe the cat also recognizes that there's a human hand there. Maybe there are other things that the cat's kind of pulling out from its observation. And then after this, the cat actually has to be able to pay attention to what's really important. This comes back to what I was saying earlier with attention. So you, for example, are able to listen to my voice and drown out any other sounds that might be around you. So here the cat has to kind of has to do the same kind of thing. It has to potentially ignore things that are in the background that are not helping it solve the immediate task that it's currently focusing on. Now, another very cool thing that we probably take so much for granted is object persistence. So the cat can't see the ball anymore once it's gone under the cup, and yet it still continues to track the cups. And this is because the cat has an understanding of object persistence. And that means that even when it can't see an object anymore, it knows that it's still there. And this is something that we actually learn as very early on as infants, that objects persist even when you can't see them. And then memory also plays a role here as well. And then finally, maybe the cat has some sense of reward attached to the object. So for example, the cat knows that if it remembers where that ball was, then its owner is going to give him a nice stroke, and maybe he'll get some extra treats later on. And so these are the kind of skills, or the kind of aspects that I'm personally really interested in kind of building into agents. And again, these might seem very obvious and very simple, but it's actually really very difficult to do a lot of these things. So one of the first things we identified was that actually, in order for these models, in order for the cat to be able to track objects, it first actually needs to be able to extract these objects. It needs to be able to decompose the scene down into objects. And there are models already that exist that are able to do this really well. I put one example at the bottom here, Monet, developed by Chris Burgess at DeepMind. But there are other great examples of this. So given some kind of observation, one frame, this model was able to decompose that scene down into the different objects. It can extract this window. It can extract this toy car. It can extract this table, or this green box. And what I've been doing in my own work is working out how can we actually keep track then of these objects across time, even when we might not be able to see them. Even when at the first time step, for example, we might not be able to see all the objects, and there might be new objects coming into our view and other objects leaving, only to reappear later. So one of the things that we did was we actually applied this object extraction model to a number of frames in a video. And so that's what you're seeing here. So you have your frame, we get objects, and you see that these objects appear in different, you can think of these as maybe slots or boxes, but you see that they're moving randomly, and it would be very hard to keep track of them like this. So what we did was we created this model to actually be able to keep track of these objects across time, assigning each object to its own box or slot across time. And what's very cool here is if you look at this frame here with the window in it, even though that window disappears for a few frames, it still reappears in that same box later. And that's really cool because this is kind of capturing object persistence. And if you're interested to learn any more, this model is called AlignNet, and there's a paper on arXiv under this title in the bottom right here. So how does AlignNet actually work? So let's imagine that we've seen a few frames at this point. So we have some examples in memory. We have some memory of observing these green objects, of the window, of the table. And now we see, we get a collection of observations from the current time step. And so we see this table here. And what we can do is we match it to something, the most similar thing that we saw in memory. And then we know that goes in the bottom slot because that's where the tables all are. And then we update the memory with this observation. Great, and then we can do the same thing for the next object in our observation. So we see the window, we pair it with the other examples of the window, and then we put it in the second slot. And similarly, we update the memory, and then we're now able to do the same thing for this green object. We recognize, okay, that goes in the top slot, and then we can update the memory again. So what's really key here is that because we have this slot-wise external memory, this is really what's allowing the model to capture object persistence and know that objects persist over time and provide something for the model to match current observations up with. So one thing that we talked about when we were talking about how to train deep learning models was we needed to have some way to compute an error or a loss, and that was one of the things that's really critical with this model. So if we have observations that are already aligned, so we had some previous observations, we aligned them using our model. And then we also have some current observations, which we aligned using our model. Then what you might notice is that observations from the previous step, plus some kind of delta. So we predict where that object's going to be at the next time step. This actually should give us the same output as if we align our current observation. And this is actually what allows us to compute an error for training this network. And this is kind of a classic example where something like classification, it's very easy, or let's say relatively easy, to define a loss. Like we have targets and we have predictions and we just want to minimize the difference between them. But sometimes we have to come up with slightly more creative ways to find the way to compute a loss. Okay, and so the underneath all that, AlignNet is really made up of all these deep networks. So how exactly does this work? Well, we take our current observations and the memory, and we use these to get the aligned current observations. And for anyone who's more familiar with deep learning, this specific model here is a transformer. And then we take our previously aligned observations and an action, and we predict where those will be at the next time step, which, as we said before, should hopefully match up with our current aligned observations. And so we can compute an error this way that we can then use to train our model. And again, for more details on this, you can check out the paper. But really, the key takeaway is that our model can endow an artificial agent with some object tracking capabilities and, more crucially, an understanding of object persistence. We're really hoping that this will enable agents to solve more complex tasks involving objects. And this actually brings me to the end of my talk. Thank you so much for joining. And if you have any questions, I would be very happy to answer them. Thank you.
Thank you so much, Toni, for your talk. It was incredibly insightful. We do have a lot of questions, far too many, so we'll have to select a few out. And I know you have to go soon, so we'll try and rattle through as many as we can. So let's start off with a question from Owen Connors. A rephrasing of this question is, do we have the structures in place in artificial intelligence at the moment to you spoke about the Atari network that was able to play all of these games. Do we have the structures in place at the moment, do you think, to be able to apply a sort of general intelligence to games where we could perhaps build a system that could play all games? Is that something you think is in the reach of AI now, or do you think that we're going to have to go back to the basics and go off on some other tangent to try and solve a problem like that? Because I'm aware that that's approaching on a kind of generality there.
Yeah, so this is actually such a difficult question to answer for many reasons. So in AI, there are many different thoughts. There are some people who think that if we just throw enough data at the problem, then we can solve any kind of problem. So they might argue, oh, well, if you train it on all games, maybe it will solve them all. Other people might argue that that's not possible and that we actually need to still come up with what people call architectural biases. So these are things like the relation network, actually, that biases a network to be really good at a particular type of reasoning. So this kind of relational reasoning. So that might not directly answer your question, but I think that is in a way an open question. And then you also even have the question of like practicality. So, can you get enough games together? Can we train agents in a reasonable amount of time? It's a good question. hopefully that kind of gives an idea of the answer.
Fantastic. I'll pass over to Shannon for the next question. If you end your presentation, Toni, then we'll, no, it's not a problem. We'll just pop all three of us up. Shannon, did you want to grab the next one?
Sure. Just as I look through the questions, I'd just like to ask a question of my own, if that's okay. So this is about the relation network that you mentioned. And when you talked about learning systems recognizing cats or dogs, you mentioned the question, how do we describe the differences between cats and dogs? And so I wondered, is this something that we could apply relation networks to answer this question? And is it better for a learning system to learn differences between cats and dogs rather than features individually?
Yeah, so this is a really interesting question. And I actually think it goes beyond relation networks. So there is this this form of learning called contrastive learning, and it does exactly this. So it will take, at the very high level, let's say, it will take an example of a dog, and it will not just learn to classify that it's a dog, but you can also train it to say what it's not. So you can say it's different from all these other examples, say in a collection of your data set. So you might have the one thing you're trying to label or make some other kind of prediction about, and then a whole load of another examples, and you're trying to train it to know that it's not that. So that's a great question, and it's definitely something that people think about. But yeah, that's a really, really good question.
Fantastic. The next question was, what do you think is the most difficult human intelligence characteristic that you spoke about at the start, these sort of facets of intelligence? Which one do you think is the one that we're going to crack the very last, if you think we're going to crack all of them at some point in time, which is a question in itself?
Yeah, that I actually worried this might be a question I got after I put that up. So yeah, that's a really good question. Obviously, the one I find most interesting is the perception problem, which is why I work on that. But a lot of people, I think, would say that the hardest problem is the transfer problem. And it's just something that we really take so much for granted as humans, that we really are able to learn to do something in one situation, and then we can do it in many other different situations. And this is just something that does not come easily for agents. There's something called meta learning, which is very cool, which is literally like learning to learn. And this is kind of a promising approach, but there's still so much more to do there. And I think a lot of people, if you ask them what is the biggest challenge, I think they'd probably say transfer. Because it's such a key feature of our own intelligence that we can really be shown like very few examples of something, and then immediately we can recognize them in other things. So I think transfer is probably a safe answer to that question.
And also probably the most interesting, because if you look at all the different avenues you can take in all of these incredibly difficult problems down all of the certain strains, trying to solve all of them takes a lot of PhD researchers, a lot of time, and probably an indefinite amount of time. So if we could meta learn how to learn, we wouldn't have to necessarily solve these discrete problems. So that's incredibly interesting. Shannon, did you have a question?
Yes, a question from Amira. Human perception often overcorrects things, and so we get deceived by optical illusions. Is it possible that an artificial agent would be deceived as well?
Yeah, that's a really good question. Again, another really difficult one. So actually one of the reasons why humans get fooled by optical illusions, there's a really great one actually, I think, where they show these triangles, and your brain's automatically able to fill in the missing gaps to realize that there's a triangle there. And that's actually a really cool ability. And it kind of comes to back to this kind of generalization. because you know triangles so well, when you see that observation, you automatically kind of fill in the gaps. And actually, if our agents could do that, that would actually be quite cool. So yeah, I don't know exactly if that answers the question, but I think a lot of the things that catch us out in optical illusions are actually us filling in the gaps. And that's quite often what we want our agents to do. So yeah.
Fantastic. A more general question. Tom was wondering, when you're working at the cutting edge of AI, as you are, what sort of languages, frameworks, tools are you using every day, just as out of interest in your sort of work?
Yeah, I don't know so one of the frameworks that we use is TensorFlow. Sure. And I think that's quite broadly known, but I think, yeah, I probably can't give too many details.
Okay, sure. No, that makes sense. That's not a problem. A question that was kind of on a similar vein to that one was by Anish, who asks, what do you think is the biggest contributor at the moment to the growth of AI? Is it the better hardware, or is it actually better algorithms? Is it new paradigms, or simply an increased investment and sort of attention to the problem? What do you think is the most important?
That's actually a really great question as well. I think probably all of those things play an important role. So, like, for example, if we didn't have GPUs to train our models, it would just take us so much longer to get any kind of research done. So I think GPUs are a really important part of it. The question about new paradigms, that's really interesting, and I think that's in a way, again, kind of a question a lot of people ask. So I mean, kind of up for debate. So again, there are some people who would argue that as long as you have enough data and enough compute, you can learn anything. But other people might say, actually, we still need to kind of have new learning paradigms, have different models that can do things like relational reasoning. So yeah, I think that it again depends a little bit like which camp you're in.
Fantastic. Shannon, did you have a question?
Yeah, so I think I'll tie two questions together actually. So Silicon Sloth says, are there other technologies aside from deep learning that you or DeepMind think have potential or are working on? And Emily Herpain wants to know more about your research and your role in DeepMind.
Okay. So the first question is, I guess, quite difficult to answer. I think a lot of the published work from DeepMind does focus actually on using deep learning. And then, so the second question, sorry, was about what my role is like. Yeah, so that's a great question. So I'm a research scientist, which means that I spend my time doing research, and that really involves kind of coming up with new ideas, having like overarching research goals, and then going away, like kind of prototyping them, running some experiments, working with other people to kind of create the right data sets and environments to try out my ideas, and then eventually getting some results. Usually presenting them with to an audience, and then either we continue that research or we start some new direction. So that's typically what it's like being a research scientist.
On a similar sort of vein to that question, where do you think, or how do you think students could best get involved in the kind of work that you do? If we're talking about 19-year-olds at university, first years, they're just going into their degrees, whether it be maths or computer science or maybe a non-STEM field. What sort of things can they be looking at now? What can they be doing in order to perhaps be able to do the role that you do, research scientist work at DeepMind in the future? Where's the sort of trajectory from here to there?
Yeah, so there are two things. So one is to actually kind of get more into AI, and the other is to be actually a research scientist, because you can be in AI without necessarily being a researcher. So in terms of getting into AI, I would say like there's so much resource online, so much more than even when I was at uni, which was not that long ago. But so there's really so much opportunity just to go on GitHub, find out some cool models. Usually they have links to their papers and also blogs. Blogs are a really good way of like getting to understand someone's paper in a very accessible kind of way. And there's normally even code with those blogs as well that they like talk through. So that's a really great way to like get into AI. And you also don't need a lot of compute to get started with. Like a really classic data set is MNIST. And it's these hand-drawn characters, and they're like 28 by 28 and black and white. So they're very small. And you can try all kinds of different algorithms out, all different kind of deep learning models out on this data set, probably just running on your like laptop CPU without any issues. And then in terms of actually being a researcher, that I would say is a slightly longer path in a way, at least it was for me. So maybe in general, it's not always essential, but so I actually did, as Joe said at the beginning, a PhD. And there I really developed my research skills. And one of those skills you kind of learn when you're doing research is actually how to come up with research ideas, how to test them, and also how to present them and communicate your ideas to others. And I think these three skills, probably even the last one might even be one of the most important, are really important for actually the research side of stuff. So if you want to be a good researcher, you have to develop these other skills as well. And that can take a long time. And at least for me, that was a very steep learning curve, yeah.
Fantastic. On that note, I think we'll draw an end to the discussion. I want to say thank you so much, Toni, for coming along to talk to us. If you want to get involved in more AI discussions such as this one, be sure to check out all of the links in the description. Toni mentioned that the best way to get involved in the work that she does is to start studying AI now. So come and join Warwick Artificial Intelligence Society, come along to our events. We have a social tonight at 7 o'clock. We're going to be talking about the 4 big topics in AI. So if you want to meet like-minded students who are also interested in artificial intelligence, then make sure you come along. Just before we go, I want to ask you about your favorite question that you received today. So I'll just go over them briefly, and then if you pick one for me, that person will win our hoodie. So we had the question about games generality, whether we'll be able to create an agent. We had the hardest human intelligence characteristic question. We had the illusion question about deceiving neural nets. We had the question about what's led to recent growth in artificial intelligence. And we had the question about the technologies that you use in artificial intelligence and at DeepMind.
Yeah, I think Joe's probably better if you pick the winner. I don't think I should pick, yeah.
You don't want to pick?
No, you should do it.
Okay, I'm going to pick the question that was about games in generality, whether we'll be able to crack the generality or whether we'll be able to sort of create an agent that could solve all games in the near future, because I thought that led to an interesting discussion. So thank you very much, everybody. And that is the end of today's discussion. So we're continuing the summit tomorrow. If you tune in at 10 o'clock, we're going to be talking about strategic AI with a researcher from the University of Warwick. So I hope to see you all there. Thank you very much, guys.
Thank you.